Hi everybody, welcome to another video in course Algebra, section 8.3, Geometric Sequences. Geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. So this is like arithmetic sequence, but instead of adding a common difference to get to the next term, we multiply to this term by a common ratio. To get to the next term. So we don't have any formula for that, but it's better to do it without a formula. So let's say write the first four terms of the geometric sequence. The first term is 6 and then multiply by 1/3. So if the first term is 6, now we multiply by 1/3 to get to the next term. And that 6 times 1/3 will be 2. So we multiply by 1/3. And then keep doing that. And we just take the 2 times 1/3. And keep multiply one more. So that is the first four terms. Right. Of course, we can also rewrite this as A1 times R, right? A1 is 6, the first term of R, common ratio 1/3. Now, this we can say A2 times R, right? A2 is 2 and R is 1/3. Now A2 is A1 times R, so we can say A1 times R, or A1 times R squared. That is A3. Similarly, here we can say A4 is equal to A1 times R cubed. So, if we see, we start from the first term, multiply 1, 2, 3 factor of 1/3, get us to the fourth. So in general, the formula recursively is A sub n equal to the previous term times R. But in general, we can say A sub n is equal to the first term times R to the n minus 1. So we take one less step to go from the first term to the n term. And this step we multiply by the common ratio. So we're going to have the first term and the common ratio. In that case, the n term is just take the first term, multiply by R to the n minus 1. Right, so that is the formula, very straightforward. Now write the first 7 terms if A1 is 3 and R is -2. So that should be easy, straightforward. A sub n equal to A1 R to the n minus 1. Now the 7 for n. A1 is 3 and R is -2 and n is 7. So we have 3 times -2 to the 6th power. So 3 -2 to the 6 is 64. And that is 192. Alright. Next, write a general n term A sub n and use this to find A of 6 if this is the case. This is a sequence. And we see 9, 3, and 1. So pretty much we multiply by 1/3 to get from this one to the next. And multiply by 1/3. The first term is 9. So we have A sub n equal to A1 times R to the n minus 1. A1 is 9, R is 1/3, and n minus 1, right? Now we want to use that to find the sixth term. Just simply put 6 in for n, we have 9 and 1/3 to the fifth. Of course, we can do this using the calculator, but I just do it by hand here. 9 is actually 3 square, right? And the fifth goes to the top, the fifth goes to the bottom. Right, so we have 3 square over 3 to the fifth. So when we divide, we subtract the exponent. 2 minus 5. Negative 3. And bring to the bottom. Become positive. And that is 1 over 27. Of course, you can just evaluate using the calculator here. 5 times 1 divided by 3 to the fifth. Right. Hit math, convert to fraction. Right. Simple enough. Next, find the sum of the first n term of a geometric sequence, knowing the first term and the common ratio. So, the sum of the first n term of geometric sequence is given by this formula. Now I'm going to attempt the proof for this. So it's nice later on if we happen to forget the formula, if we know the proof, that will help. I always said it's better to do the problem without the formula. Intuitively is the best way to do it. So let's say geometric sequence. We have the first term, the second term is the first term times r, the third term is the first term times r cubed, and we have these two, r to the n minus 1. Right? Now what we do is we multiply everything by n. Everything by r, and I'm going to put that on the top. Right? Let's do that again. Because if I can count correctly, right, so this is just the same thing, right? Now what I do is I will multiply r on the top on both sides of the equation. Right, if you multiply by r, you have that. And this to the second, this to the third, and the last term is to the n. Right? Multiply everything by r, that's what we have. Now, the second equation, I multiply by negative 1, so turn this to negative. And then if we add side by side, we have r s of n minus s of n equal to, notice that now we have a1r minus a1r, a1r squared minus a1r2. So pretty much everything cancels out, except we have the negative a1 here. And everything cancels out, except this 1 to the n. There's nothing to cancel with that. Now if we factor both s of n out, we have r minus 1. And I will write this a1 r to the n minus a1, factor out a1. So that gives us, if we want to solve for s of n, is a1 r to the n minus 1 divided by r minus 1. And so that is the proof for that formula. The other formula is the same thing, we just subtract it the other way. Take the second line, subtract the first one, but this is the proof. Right, now let's find the sum of the first 7 terms of the geometric sequence. In this case, this geometric sequence we see is that the first term is 2. The common ratio to get from this term to the next, we multiply by -4. And then we just have that geometric sequence. So the sum of the first 7 terms, let's just write the formula. R to the n minus 1, r minus 1. Now, we want the sum of the first 7 terms, so 7 is equal to n. A1 is 2. R, common ratio is -4. N is 7 minus 1 over -4 minus 1. That gives us 2. -4 to the 7 power. And then minus 1. I don't need calculator for that. -16,385 divided by -5. So we have 2 times 3277. 6554. Right. Simple enough. Next, evaluate this sum. Of course, we're going to put 1 in there. So we're going to have 2 times 3 to the first, 2 times 3 square, and all the way to 2 times 3 to the 8. Right? So this looks like a geometric sequence because we multiply 3 every time. So when we write like that, in this case we have the first term is 2 times 3 to the first, which is 6. And the common ratio to get from this term to the next is we multiply by 3. Right? And we go from 1 to 8, so that's the sum of the first n term. So s of 8 equal to, I'm using that formula again, a1 6 times r to the n minus 1 over r minus 1. And that minus 1 shows 6560. Divided by 2. $65.60, sorry. Six and 2 cancel out, so just multiply by 3. 19,680. Of course, if we want to check math, use that option. Equal to 1 to 8. And I would just say 2 times 3 to the x power. We should get the same thing. Right. Next, we have the sum of geometric series. So the sum of all the terms in an infinite, so the difference here is going to be an infinite sequence, so it go on forever. For geometric sequence with the first term a1 and the common ratio r, so this will be the same. We have the first term, we have the common ratio. What not the same is r have to be between -1 and 1. The sum of geometric series is a1 times 1 minus r. Alright, why is that? Now let's look at either one of these formula. Look at the first one here. If r is a very big number, like, I mean not very big, bigger than 1, like 2 to the n power, bigger the n, so this one will go to infinity. If r is bigger than 1 or less than -1, this will go to infinity. So the sum does not exist. Now if we look at the other way around, if you have 0.5, when we square it, that's 0.25, and when we cube it, it's 0.125. So the higher the power, the closer this gets to 0. So if this gets to 0, that's what we get, a1 times 1 over 1 minus r, which is just a1 times 1 minus r. So be mindful that r has to be between -1 and 1 for this to work. Alright, now let's look at this. Find the sum of the following geometric series. So in this case, of course this is the geometric series, geometric sequence, but the sum goes indefinitely. So the dot indicate go on forever. So for this geometric sequence, we write out the first term is 1, the common ratio. To get from this term to the next, we start from 1 and then 0.5, then 0.25. So that pretty much the common ratio here is 1/2. And the sum of the geometric sequence, we can put infinity here if we want to, but if we want a particular sum of the first n term, we're going to put n there. For the geometric series, for indefinite geometric sequence, the sum, we don't need to put anything there, just s. The first term times 1 minus r. Just make sure that whenever we write r, just do the little check between -1 and 1. If it is the case, yes, so we can multiply, we can add them. a1 is 1, r is 1/2. This, I can just multiply everything by 2. Give us 2, and 2 and 2 cancel out, so that on the top is 2, right? Sorry. 2 times 1, 2, and 2 and times 1, 2 and 2 cancel out is 1. So we have 2 over 1, which is 2. So this sum is equal to 1. I mean, equal to 2. Alright, next. We have this. So let's write out what we have. The first term is 2. Common ratio. To get from this term to the next, we multiply by -1/2. Sorry. It's going to be negative for sure, but it's not. It's -5 over 4. Fine. Now if we don't know that, it's fine. Just write out 2 multiplied by r is equal to -5 by 2, right? We multiply by r to get from this term to the next. So that's what we have. Now multiply both sides by 2. We have 4r. 2 and 2 cancel out. So that's where we multiply both sides by 2 and then divide both sides by 4. We have r equal to -5 over 4. Right? And then as always, we check to see if the ratio between -1 and 1. And -5 over 4 is -1.25. So which is not. Because of that, we say the sum of the geometric series does not exist. Right, so be mindful with the case when the ratio is not between -1 and 1. Right, next, convert the following to decimal from decimal to fraction. Right, so this is indefinite. Of course, the easiest way is we just do that and convert to fraction. There, right? But let's just write out 0.777. If I write it as 0.7 plus 0.07 plus 0.007, right? That certainly is. So this is the geometric sequence where the first term is 0.7. The common ratio is 0.1. Right. Now, with that, we can see the sum is equal to A1 over 1 minus R. And of course, we should check that to make sure that the ratio is between -1 and 1. So in this case, 0.1 certainly is. So we can use this formula. By the way, we know we can use this formula because the sum exists equal to that number. If it is not, then it does not exist. But we know it exists equal to that number. Right. The first term, 1 minus the common ratio, 0.7 times 1 minus 0.1, 0.9. Multiply top and bottom by 10, we have 7 over 9. Right? Next, so that. So if we rewrite this as 0.12, now the thing is this time we have 2 digits repeating, so we're going to skip 0012 and then skip. So differently, this time the first term is 0.12. The common ratio though is 0.01. So for 2 digits repeating, we have to skip 2 zeros. Right. So sum is equal to A1 times 1 minus R. So A1 is 0.12. And R is 0.01. So we have 0.12 divided by 0.99 multiplied by 100, or move to decimal place 2 places to the right. And we have 12 over 99. Over 99. Now notice that if we have 1 digit repeating, that's 0 point the repeating, then we're going to have 7, 1 divided by 9. If we have 2 digits repeating after 0, that will be divided by 99. So with that pattern, I can say for sure 2, 3, 5 like that. It's going to be 2, 3, 5 over 9, 9, 9. That only works if it is repeating right after the decimal point. And then there's just 0. In general, there's a much better way to do that. Let's set the 1 without the formula. Anyway, we need to reduce this by 3. So 4 over 33. So that certainly works. Now, so that is where we use the formula. Again, if we use that formula, make sure the ratio is between -1 and 1. Which is the case because that sum exists. Right. Now, a better way to do this is without the formula. I'll just do this again. 0.7 is 0.7777, right? What I do is I'm just multiply this by 10. 10 times 0.7, repeating. Multiply everything by 10, I have 7.777. If we subtract, you have one of them, subtract this, you have negative 9 times 0.7. And subtract this, all the decimal place cancel out. We have negative 7. And solve for it. We solve for this. 0.7 repeating is 7. Negative 7 over negative 9, or 7 over 9. Right. So that, of course, is similar to what we did for the proof. And we don't choose any formula. The nice thing about this is we can do let's say something like this. Remember, if there's the 1 on the top, we cannot just say 1, 2 divided by 99. It's not going to work. But now if we multiply by 10, you cannot do that. We have to multiply by 100, because in that case, because there are 2 digits repeating, we have to multiply by 1 followed by 2 zeros, so 100. If 3 digits repeating, we're going to multiply by 1000. So this time I multiply by 100. So that gives us 112. And then the decimal. And if we subtract this, the second line to the first line, we have 99 times that number. All the decimal cancel out. 112 minus 1 is 111. So we have 1.112 repeating is 111 over 99. Alright, let's see. 1.12121212. Of course, I forgot to reduce this by 3. Right, like I said, the better way is to do it without a formula. So if there's 1 digit repeating, multiply by 10 and subtract them. 2 digits repeating, multiply by 100 and subtract them, and then so on. So with that, I finished section 8.3 here. Thank you for watching, and see you in another video in course algebra.